Now we were discussing about the straight line mechanisms. So as I just told in the previous video that slider crank is one of the mechanism for the generating a straight line from a rotary motion of the crank. However, because of the lateral thrust in a slider crank, you have friction and losses and the machinery becomes heavy. So there are many other mechanisms which can be used to generate the straight line to the rotary motion and vice versa. So I'll just illustrate some of them for you. First, we will consider the straight line exact mechanisms, exact straight line mechanisms, and then we'll come to the approximate straight line mechanism. The first one in this category is the Porcellius. I will draw a sketch for you. So this mechanism is formed by a simple 4-bar chain which is isosceles also. That means the links are of equal length, the adjacent links are of equal length, and the length of this adjacent links are equal. So it is a kind of deltoid mechanism. Then in this chain you have an additional link. It is connected like this. So a link is formed here, and one link is having a rotary pair with respect to the fixed link, that is ground, and it is going extending all the way touching this link, and there is a center connection. This link is formed in such a way that these three points fall in a straight line. A straight line is formed. This is a special property of this mechanism. I'll give you some names to these points, kinetic pairs. Link OA, maybe this is B, C, D, E. So like this, I'll name the point. So here, this link OA, this OA is the driver crank. This is where you get the rotary motion at the link OA, and you get the straight line motion at C. So this, here you get the straight line motion, here you get the rotary motion. So depending on the direction of the rotation, you will get up or down straight line motion of the point C. This straight line will be perpendicular to the line connecting E and O. So C is the point traversing the straight line. So as you can see in this mechanism, all the pairs are rotary pairs. There are no sliding contacts, and from a rotary motion of the link OA, you can get a straight line motion of the point C. The derivation of this straight line, whether the C will, how the C is going in a straight line, is very simple and it is available in any standard textbook. We don't need to consider it in detail here. We just need to know this mechanism for now. So what kind of mechanism is a Porcellius mechanism? Such kind of questions may come in GATE examination. So you see in the Porcellius mechanism that the adjacent links are of equal length. So such kind of simple questions, objective questions, can be derived from the names of the straight line or any other mechanism. That's why we are studying these here. The derivation of how the straight line is formed, that is not important from the GATE perspective. Another category in the straight line motion, exact straight line motion, is the Hart's mechanism. So here we have seen earlier in GATE examinations, some questions have come that Hart mechanism, it comes under which category of straight line motion mechanism. So this is exact straight line mechanism. So I'll draw a sketch for you of this mechanism. Basically, it's an inverted parallelogram. So as you can see here, this is an inverted parallelogram. We'll term this end as O, P, Q, R. So the nomenclature may be different in different textbooks. You can go and find much more details on this mechanism in the textbook. So this is an inverted parallelogram. This is inverted parallelogram. That means the opposite links are of equal length. This is S, this is S, this is L, and this is L. Now on this link, the longer link, you can choose any point named B, and of the same length, the length BB, you can choose a point coming from R on this mechanism termed as A. So PB is equal to RA. So the same distance, you have to choose a point. Then if you connect AB by a dotted line, it will go and cut the line PQ at some point T. Let's say T. So the definition is such that if you make a circle passing through T and A, then if the A is constrained to move in such a manner that the circle touches the point T, then the point B will have a straight line motion. So this link, this is a chain, kinematic chain. You have to anchor it somewhere. So the point R in this chain, the joint R, is anchored to the ground. Okay, so it is such like that there is a circle going from A. The A is going in circle, and T, and it is touching that point T, and somewhere you will get a center of the circle C. So the motion of path B will be perpendicular to the line TC. So it is somewhat complicated derivation you can see in standard textbook. But from the gate examination point of view, you just need to know that a hard mechanism is an inverted parallelogram 4-bar chain exact straight line motion. So this is what you should be aware of. The third category in the exact straight line motion mechanism is a Scott-Russell's mechanism. This mechanism actually employs a sliding pair. So it is not truly speaking a rotary link kind of joint. I'll draw it for you. So you have a sliding pair mechanism, which is a extension of the 4-bar mechanism. We will be covering in much detail in coming videos. And this is a crank. OA is the crank. This is O, and this is the fixed link, and this is the sliding pair. You have a sliding surface. It is rotating, it is sliding. So this itself is a straight line motion mechanism. However, if you extend this connecting rod in such a way that it comes and intersects the straight line somewhere here, in such a manner that OA and this point is B, in such a manner that OA is equal to OB, this length OA is equal to OB, then while the crank is rotating, OA is rotating the crank, then B will be moving in exact straight line. Okay, So you have exact straight line motion. You have constrained the piston, the sliding pair in a straight line motion. So C will anyway be moving in a straight line. But if you extend it such a way that OA is equal to OB, then B will also be moving in a exact straight line. So this is the third category of the exact straight line mechanism. The second category of the straight line motion mechanism are the approximate straight line motion mechanisms. In this category, we have the Watt's mechanism, the Grasshopper mechanism, and the Roberts mechanism. So first we consider the Watt's mechanism. I'll draw a sketch for you. So it is basically formed from three main links. It is also a 4-bar chain, but the fourth link is fixed. So 3-link chain. This is anchored to the ground. This is one rotary joint. This is another rotary joint. And this is a third anchored to the ground. So this point will term as O, this A, this B, and this may be O dash. So the theorem given is that for this mechanism, a point P can be found on link AB, which follows approximate straight line for a limited travel of the mechanism. So you can have the rotary motion input from the link OA, this can act as a crank, or you may have it from the OB also. So OA or OB is the crank, and you can find a point P, not all the points, some points based on some geometrical derivation that you can find in textbook, that it follows approximate straight line over a limited period. Not like the entire crank revolution will not be possible. It will not be traversing a full straight line, but for some limited range it will follow the straight line. That's why it's an approximate straight line mechanism. So in the Watt's mechanism, we don't have any special condition that length of any link should be equal, like the OA should be equal to OB or something like that. We don't have any such condition. It's a generic mechanism where you have two cranks and they are connected by a coupler, and the motion of the coupler will be a straight line over some limited period. So it's a general property. It can be used. It's a generic mechanism, and it can be used in analysis of other mechanisms. The use of these properties can be made. So in examination question can come like Watt examination, Watt mechanism is which kind of straight line motion mechanism. You can tell that it's approximate straight line motion mechanism. Now we will go to the Grasshopper mechanism. It's a variation of the Scott-Russell mechanism. So if you recall the Scott-Russell mechanism, it was a crank chain mechanism. Here you have the sliding pair. This is the crank, and this line we extended such that this OA is equal to OB. So we extended such like that, and this linear motion of the piston is present, and the linear motion, straight line motion of the B is present. In the Grasshopper mechanism, we will replace the sliding pair by a turning pair, like we have a typical 4-bar chain. So you have a typical 4-bar chain like this, and then you will extend this link such that OA is equal to AB. So you will extend it such like that, and there is a special property. So while in the slider crank you had the link C as a sliding pair here, you in the grasshopper you are having the rotary pair. So it will have a rotary motion mechanism. At the exact 90-degree position, it will have an approximately horizontal motion. So the special condition needed in this mechanism is that OA is equal to AC square by AB. So if you are fixing the length in such a fashion that this condition is satisfied, then the motion of the point P will be an approximate straight line for a limited range. So it is also quite generic mechanism. You don't have any special properties here. It's a simple 4-bar chain, and the motion of B is approximate straight line. This property can be used in analysis of many other complicated mechanisms. So what we had for the Watt's mechanism, that a simple chain is formed like this, and the point P will have approximate straight line motion for some period. Similar property we have for Grashof. Is a 4-bar chain. The B will have, if this condition is satisfied, for a fairly long period of motion, you have approximate straight line. That's why it is important to study. The third category is the Roberts mechanism, which is nothing but a simple 4-bar chain, OABCD. So in this, the special condition satisfied is OA is equal to BC. Only this condition needs to be satisfied. These links need not to be equal length. So this need not to be a parallelogram mechanism. Just OA should be BC. Then if you draw a line through the right bisector of AB, and also if you extend this OA and BC links, they will intersect at some point, say Q, and from this Q you draw a perpendicular to OC. These two lines will go and intersect at some point P. So the point P will have approximate straight line motion. So there is derivation, you can look in textbooks, and you know that in Roberts mechanism this condition is satisfied. It is a simple 4-bar chain. What you have observed here in approximate straight line motion mechanism is that all of them are simple 4-bar chains, and there is a special property from criteria satisfied, like OA is equal to AC square in the Grashof mechanism, and OA is equal to BC in this Roberts mechanism, and then you can get a point. In a Watt mechanism, no special condition, but you can get a point in the coupler link such that it follows the approximate motion. So these definitions come handy in analysis of other complicated mechanisms. After discussing the straight line motion mechanism, we come to another category of mechanisms which are used in steering gears. So those mechanisms are known as steering gear mechanisms. The steering is considered here in relation to 4-wheeled vehicles. So I'll just draw a sketch to explain what is special about a steering mechanism. In a 4-wheeler, you have 2 axles. One is the front axle and one is the back axle. The axles are having wheels on its other side. So you have one wheel here. So these are the front wheels of the 4-wheeler, and then you have the back wheels. So the condition for steering is that at any instance of time, Like in the when you are steering the vehicle, normally the front wheels will have a angular displacement. Because of that, the vehicle will turn. So the condition for steering is that at any instance of point of time, the centers passing through the perpendicular line through the wheels should be intersecting at a common point. So all the four wheels, if you draw a perpendicular line through the centers of the wheel, they should be coming and intersecting at the same point. This point 4 is known as instantaneous center of rotation of the vehicle. Why this condition is important? This is because if this condition is satisfied, then all wheels will have pure rolling motion. There will be no sliding motion. So the wheels would not be skidding. The skidding will lead to friction on the wheel and wear of the wheels. So that's why we need pure rolling motion. So if any of the wheel is not, let's say this wheel, in this picture it is drawn like that, it is having motion in this direction, while the instantaneous center of the vehicle is such that it should have a motion in this direction. So if this wheel is moving in another direction, there will be a sliding as well as rolling motion. Both kind of motions will be present, sliding as well as rolling. So rolling motion is desired of a wheel, but the sliding motion is not desired because of wear. So the condition is axis of rotation of all wheels should pass through a common point, that is called the instantaneous center of rotation. So now for achieving this condition, you need to have a particular mechanism which can help us to achieve this thing. So we will consider those mechanisms here. The steering gear mechanism, we have two categories. One is called Davis steering gear and the second one is called Ackermann's steering gear. So I'll draw a sketch of both of these mechanisms one by one. We will not consider derivation here. So in a Davis, it is pivoted about a point, about a fulcrum here, and then you have a link like this and a sliding pair. There is a link which is forming the sliding pair. These two are joined together, and then they are constrained at a particular axial position. So this link is not allowed to move in this direction. This motion is not allowed. So at a particular axial location, they are constrained. This is forming a sliding pair, just like this. So if you want to steer the vehicle, want to turn say right, then you want to tilt this wheel like this and lift this like this, while you maintain the condition that the instantaneous center should intersect. Then you just move this link towards left. This link L move towards left for right turning. So the special property of this mechanism is that that this length L should be equal to this length, and this should be a symmetrical mechanism. You can turn right also if you move the link L towards left. We will not consider derivation here that you can find in any standard textbook, but this mechanism will ensure that the wheels are turned in such an angle theta and alpha. Theta and alpha are such that the steering condition that all wheels in simultaneous center should be same is maintained. The other category is the Ackermann steering gear. Here also a similar link is formed. You have these two front wheels that are pivoted about a fulcrum. This is the other side of the wheel. They are pivoted about the fulcrum. The length of these links L and L are same. These are also same. Maybe L2, let's say, L1. And these are just connected by a simple link, binary link. So the all revolute pair, no sliding contact, and a simple binary link. Here also, if you see this link in a deflected position, this is getting deflected. This chain will form in such a manner. This 4-bar chain, simple 4-bar chain, will form in such a manner that the angle of turning theta, and for this wheel the angle of turning alpha, will be such that what is the difference that you see between these two? In this one, the coupler link can get distorted. So in mean position, while there is no turning, it is like this. In a distorted position, it will look somewhat like this. So the lengths are not equal, and it can have an angular motion also. So it need not be constrained in a plane. While in the Davis gear, it is constrained in a straight line motion. Coupler link and the sliding link are accommodating for the change in radius. So it is simpler from the design perspective, that you just have to move the length, that is link L here, and here you have to take into account the angular motion of this link also, so it's difficult to control. And the disadvantage with Davis gear is that you have the sliding pairs. So because of sliding pairs, you have wear and tear and loss in accuracy of the steering. That is the disadvantage. Here the disadvantage in Ackermann is that the coupler link is having rotary motion. You have to take account of that when you are transmitting the steering from the steering wheel. So it will be transmitted from some other location at the driver's seat to this position. This angular motion also you have to take into account. And here in the Davis you have to take the wear into account. So with this, we finish the knowing names of different kind of well-known mechanisms. Now we will move forward to the sliding crank mechanism, which is the topic of great interest, and a lot of great questions are coming from that topic.